Yeah, final words to the bode plot of a PT2. Bode plot. First, I give you the function for the complex frequency response. Well, we just take the transfer function. This one. This one, where p is replaced with j omega, you see there is a p squared. You will see what happens with the p squared. So we have a 1 here plus 2d divided by omega times omega naught times j omega plus j omega squared times 1 divided by omega naught squared. In other words, this is k times, now you see 1 is the real part, that's imaginary part, and j squared is minus 1. So here you get a negative omega divided by omega 0 squared. That is the real part, plus j 2d omega divided by omega naught. That is the imaginary part of the denominator. With this, we can now discuss the magnitude of the bode plot. The magnitude of the bode plot then is magnitude of the numerator, okay, real number, divided by the magnitude of the denominator. And here now we have the following situation, that we have a real part, which is 1 minus omega, omega naught, forgotten. 1 minus omega divided by omega naught squared, and then we have to square the real part plus the square of the imaginary part, that is 2d omega divided by omega naught squared. So this expression gives the magnitude curve of my PT2 behavior. You see the real part could be positive for small frequencies, or for large frequencies negative. If omega is larger omega naught, then the real part is negative. For my magnitude, this doesn't play a role. It's still squared. What you can see more is now, the analysis of this curve can be done manually. You can look for the maximum, look what happens with the display of this curve. I show you the resulting bode plot drawing of this curve. So f in dB and the logarithmic axis of the radian frequency. There is first an asymptotical construction possible. You can say, okay, for low frequencies, the one is dominating. This is small, squared, smaller than this. Finally, for low frequencies here we have a 1 which is dominating, and k in the numerator gives the situation that we have a horizontal asymptotical curve, and here with a distance to the 0 dB line, which is k in dB. So for low frequencies we have a constant gain k. And now for large frequencies, this is neglectable. This is neglectable, and here we have an omega to the power of 4, square root of this, omega to the power of 2. So the large frequency have omega magnitude for omega is very large compared with our omega 0. We have an asymptotical curve which is k divided by omega squared omega naught squared. So this is a curve with a gradient defined by the squared function of omega in the denominator. We can show that now the gradient of this asymptotical curve goes down with 40 dB over a decade. The cross point here of the low frequency asymptotical curve and the high frequency asymptotical curve is exactly if omega is omega naught, you see, then the result is k at omega naught. So we can say omega naught is a corner frequency because then the asymptotical curves have the corners. Could be one name, but it is traditionally not the name in the PT2 situation. And now we need another special value, which is f at exactly natural frequency. This magnitude value can be calculated because the real part is 0. This is 1. 1 minus 1 is 0. Squared is 0. This is 2d times omega naught divided by omega naught is 2d. Squared square root is just a 2d. It's k divided by 2d. So this depends on the damping factor. If this point, this exact point, it's not the resonant point. This point, exactly at this frequency, could be now larger than k if damping factor d is smaller than 0.5, or this could be under this corner frequency depending on the damping factor. For large frequencies, so for high frequencies, always the magnitude curve stays here. For large damping, we have this. For small damping, we have this. And we can say, okay, this value here, this value, this distance from k to this value is 1 divided by 2d, 2 times d, again better, 1 times divided by 2d in dB. Don't forget to convert into dB. Let's do this for some d values. That is a delta f, we can say delta f. D value, delta f in dB value. If we do this, then we can find out that if damping factor is 0.5, the special value 0.5, the k divided by 2 times 0.5 is 1, so this point here, or 1 divided by 2d is 1, so we have 0 dB distance. 1 is 0 dB. Yeah. So in the case of damping 0.5, the magnitude curve goes exactly through this point. If we have larger damping, say 0.8, then I calculate the delta f value. And if you have smaller damping, say 0.1 or 0.01, you will see then we have values here which are much positive and large. I have to do this just manually in the meantime. Okay, damping factor 0.8, we get negative 4.1 dB. 0.1 gives plus 14 dB. 0.01 gives plus 34 dB. You see, then we have a big resonant peak. If damping factor is 0.7071, we get exactly minus 3 dB. If damping factor is 1, we get exactly minus 6 dB. So what we can find out is damping large, curve goes down quickly. Damping small, we have a resonant peak, and note that there is a maximum of the curve which is a little bit larger than the value 1 over 2d or k over 2d, a little bit larger. I have calculated this maximum value in my workbook. You can find the value of the maximum on the page 22. Look into this picture. Here you can find relevant values. Yeah, we talk about this point at just last minutes. I have calculated the maximum of the curve. It is a little bit larger because I have to divide with 1 minus d squared. But if d is small, then this is rather not a relevant number. And the maximum frequency is a little bit smaller than omega naught, but also this value is rather small if damping is small. This is near to 1. Yeah, 1 over 1 minus d squared, and square root of this is very near to 1. This is near to 1. So this drawing is not in a real scaling, because you will see this point and this point in the bode plot are just less than millimeter on the same position. Okay, I think this is far enough for the only thing what we can mention here is note that here the amplitude is larger, the output amplitude of the signal is larger than the input amplitude. We talk about U1 input, U2 output, and this is the sinusoidal signal at the input. This is the PT2, and this is the sinusoidal output. If our generator is near to my resonant frequency, to my natural frequency, then the output amplitude could be factor, what is this? 14 factor 5. This is factor 50. Yeah? That is factor 50. Delta F, note, not in dB. This is 1, and this is factor 50, and this is factor 5. That means the output amplitude, if I have a small damping, could be 50 times larger than the input amplitude, and then because it's a resonant effect. Resonant effects are often seen in nature. For example, we use the resonant effect in music instruments, in a guitar. The body of the guitar is a resonant body to amplify the sound of the strings. Sometimes the resonant effect can destroy systems. Look, resonant effect, Tacoma bridge. Yeah, that is a keyword. Tacoma bridge. Look into YouTube, search for Tacoma bridge. Then you can see what happens if a strong wind with a low damped bridge can cause severe problems, because there is a video, I think 70 years ago or so, which displays the damage of a bridge caused by a resonant oscillating, caused by wind. Okay.